Membrane proteins are a major part of a membrane. We've already looked at kind of the abundance of them. Yeah, lipids are a part of um, a cell membrane. Sterols are a part of them in some organisms, but proteins account for a very large amount of the weight of a membrane. Now, when it comes to proteins, those that are found within a membrane, they can do a number of different things. One of which is they can span a membrane, as we see a couple of different examples of them in these different kind of models. We'll see a peripheral protein that's found on only one side of a lipid or on one leaflet of a lipid bilayer. Then there are your integral proteins that are tightly associated with the membrane, and chances are they are embedded and threaded through that membrane. Now, in order to kind of liberate or free these, if you want to study them, for instance, you're going to have to use something like a detergent, something that's going to disrupt a hydrophobic molecule or hydrophobic compound. You also might have to use a chaotropic agent like we've already talked about chaotropic agents like guanidine hydrochloride urea is another example of a chaotropic agent in order to separate these from a membrane. Um, Lipid-linked proteins are another kind of way in which a protein can be associated with a membrane. Now, what that means is that this protein right here, chances are it has some sort of covalent modification of a lipid. So it's got a fatty acid, maybe, or a long alkyl group. So some sort of 30 carbon or 10, 20 carbon um, hydrocarbon that's super hydrophobic that whenever it gets kind of inserted into a membrane, it likes to stay there. So that lipid-linked protein is going to be one that attaches or associates with a membrane because it's got that group that kind of grabs onto it and holds it there. Peripheral proteins are globular proteins, and they're pretty easily dissociated. I know those are the ones that I started with in this description, but that's just kind of the nature of them. They're there, they're associated with the membrane, and then something causes them to release. So what that means is they're temporarily, and then at some point during the cell's lifetime, they move on, or maybe they go to the cell leaflet and then they leave it. They come back and forth. Whereas your integral proteins or your lipid-linked proteins are more likely there to stay for quite some time. Um, now, your integral proteins that span a membrane, chances are they're going to use an alpha helix, which we see here. Now, these are classified in a couple of different ways. We've got the inner leaflet and the outer leaflet here. A type 1 transmembrane helical protein has the N termini on the outside and the C termini of that protein on the inside. So those termini are at opposite sides. Type 2, well, they're going to be the exact opposite. The directionality of them is going to be reversed. The N termini is inside and the C termini is outside. Your type 3 transmembrane proteins, what they do and what's significant about them is the N termini versus C termini does not matter so much that what matters is that the N termini and C termini are on opposite sides of that lipid bilayer. Your type 4 proteins are going to be multiple polypeptides that kind of aggregate together with their N termini and C termini on various sides, but they're all going to be multiple different polypeptides. Type 5s, well, they have a lipid linkage that affixes them to the membrane. Type 6 is a protein that has a single alpha helix and a lipid linkage that kind of sticks in that membrane. Now, one of the things that I want you to really pay attention to with respect to these is I'd like you to keep types 1 and 2 straight, types 3 and 4 straight. Type 5 and 6 are a little bit less important right here because we're going to talk about them in a different fashion in just a moment. But when it comes to these transmembrane proteins, I want you to remember that this is more than likely an alpha helix. So that's a secondary structural element. And that secondary structure, if you look at this right here, this region, okay, and you might have to zoom in on this. What is the composition of those amino acids? I see an isoleucine, phenylalanine, glycine, valine, methionine. Okay, methionine's a little bit polar. Or no, I'm sorry. I was mixing up methionine and cysteine. Then you got alanine, glycine, valine, isoleucine, glycine, threonine. Threonine's polar, sure. Isoleucine, leucine, leucine, isoleucine, serine, that's also polar. But for the most part, these are non-polar amino acids, which makes sense that those are going to be making up that transmembrane domain. So if you think about, if you were to look at the primary structure of a protein and you lined up the N termini to the C termini and just looked at your amino acid sequences, and you looked at those amino acids and just kind of studied them, what you might notice is that you've got a lot of non-polar amino acids. Maybe they're clustered together. Oh, a bunch of non-polar amino acids clustered together. That might be a sign that that is a transmembrane domain. So you kind of have that prediction model built in. Now, transmembrane proteins don't have to be alpha helices. They can be made up of beta sheets. So that secondary structure can be a beta sheet, in which case you'd have things like this. Now, one of the things that I always like to visualize is this alpha hemolysin toxin. What that effectively does is that's a toxin, or it's a toxic protein. And basically what it does is it makes this little hole in the membrane. And what that allows is for nutrients or ions to basically flow out of there. So those ions are going to kind of empty out of the cell, in which case the electrical regulation of that cell is going to get disrupted. Now, if we look back here at types 5 and type 6, I want you to think about those with these little tails. These little tails are lipids. Maybe they're fatty acids, or they could be these right here. These hydrocarbons. These hydrocarbons are known as terpenoids. These terpenoids are just hydrocarbons. They're long hydrocarbon chains. And if you look at this farnesyl right here, you'll see 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15 carbons. This is 15 carbons and just a bunch of hydrogens. That is going to love being embedded in the nonpolar region of a lipid bilayer. And so if you had a protein that got this farnesyl group, or this one right here, this is a geranyl-geranyl residue, and I'll save myself the counting. This is 20 carbons long. So we got 15 carbons and 20 carbons. If you had these two different compounds, well, they are going to love being within that nonpolar region of a lipid bilayer. And they're going to love to just kind of dig in there and stick and stay. And that's one way in which proteins can get associated with the membrane. Another way is looking back at something like this. Look at this. Phosphatidyl inositol. Oh, oh, our model for a glycerophospholipid. Here's our glycerol. Here's our two fatty acid chains, 1 and 2. Here's our phosphate group. Here's that 6 carbon ring for that inositol group. And then here's, oh, this is, well, GLC, NH, man. Those are sugars. This is an aminated sugar. And then these are mannose. And then we can have this phosphate group, and then this ethanol amine, and then we've got a protein. Long story short is you can have a protein that through a very roundabout way ends up with a glycerol phospholipid linked to it. Glycerophospholipid, if I showed you just this right here, I'm going to switch colors. I'm going to change it to black. If I showed you just this structure right here that I've kind of drawn a circle, square thing around, and I told you, hey, this is a part of a membrane, you'd be like, okay, that makes sense because glycerophospholipid and sphingolipids are major building blocks of membranes. And I said this inositol, well, it's got a bunch of sugars added to it, and then it's got a polar head group. And to that polar head group, we're going to covalently bond a protein to it. Whoa. We've got this elaborate way in which a protein is basically dug into a membrane. So what I want you to visualize with this is this, if a protein has one of these two, one of these terpenoids added to it, that's going to be a good example of a type 5 transmembrane protein. If it's got this guy right here, this is going to be an example of a type 6, but we're also going to see it in a slightly different way in just a moment. Um, and this structure right here, this whole thing, that I want you to visualize as this whole thing right here. Here's our protein. Here's that head group. Here's that linkage of sugars. Here's the inositol, the phosphate, and the glycerol. This is what is known as a GPI anchor. So we refer to this as a type 6. This is also a glycerophospholipid inositol, or a GPI anchor. So a protein can get a GPI anchor, sticking it to the outer side of a membrane. Now, there are other ways in which proteins can be linked to membranes, and we'll see those on this page. So there are four major types of linkages that connect lipid linkages or lipids to proteins. One is you could have a thioester linkage. So a fatty acid can be anchored to a cysteine or a serine. So I want you to know that cis or serine. Okay, that's one place in which a fatty acid can be added. Which, if you think about, what's the R group for cysteine or serine? Well, cysteine, CH2SH. Serine is CH2OH. So that sulfhydryl or that thiol or that hydroxide group can basically be replaced by a fatty acid. You can have an amide-linked myristyl anchor. So myristic acid can be added to the N-termini of a glycine. So we can add to a glycine. So glycine. And I'm thinking about these in terms of what are good targets for amino acids, or what amino acids are good targets for modifications. Then we've got thioether-linked prenyl anchors. This is that terpenes, those terpenoids. So these are built on isoprene units, also known as terpenoids, most common being 15 or 20 carbons that can be added to a cysteine. Okay, so just to jump back here, these can be added to a cysteine. There we go. And last but not least is our GPI anchor, located only on the exterior surface of the plasma membrane and always attached to the C-terminal amino acid. So the C termini of a polypeptide. So on C term. Okay, so this gets into the kind of organization of proteins and where they can be placed, but this doesn't really talk about function, and the function can be very diverse. For instance, diverse, I didn't say diverse, but it can be very diverse. Specifically, if we look at this GPI on the bottom, what's cool about this is this protein, this GPI anchored protein, is basically displayed to the exterior of the cell. It's ready to go. It can act on anything it wants. Now, one thing that a protein, a membrane protein can do is it can be involved in transport. Now, there's two major types of transport. There's primary active transport and there's secondary active transport. Now, what is being transported varies tremendously. There's ions, there's sugars, there's any number of molecules that can be transported from one side of the membrane to the other. But here what we have is primary active transport. This is an enzyme that is moving X, a compound X. It doesn't matter what it is, X. It's being moved into the cell. Now, what I want you to notice about this X is outside of the cell, right here, the concentration of X is very high. Inside of the cell, it's very low. So what that means is that this X is moving against its concentration gradient. So it's moving from a high concentration to a low concentration. So an unfavorable move. Now, in order for that to happen, you're going to have to hydrolyze ATP. So you're going to couple the hydrolysis of ATP, so this high energy bond, this phosphodiester linkage, or no, um, this linkage between your beta and your gamma phosphates. Whenever you break that, you release a lot of energy. And in this case, this enzyme is going to harness that energy and move X Sorry, it's moving X from a low concentration to a high concentration. So an unfavorable move. So it's moving it out of the cell, not into the cell. Okay, so in order for that to happen, moving against its gradient, you have to kind of provide the energy for that. Then we've got secondary active transport. Secondary active transport consists of two enzymes. It is moving X, or one of them is moving X from a low concentration to a high concentration. The other enzyme is doing two things. So this first enzyme is not so different from this one over here. It's using X going from a low concentration to a high concentration, and the hydrolysis of ATP to drive that. This other enzyme right here, though, well, that's moving S, another molecule, from a low concentration to high concentration. So the movement of S, frown face. The movement of X, well, it's frown face, but plus ATP hydrolysis makes it smiley face. Okay, so it makes it favorable. Now, S, let's look at this. Well, this protein right here is what's known as a symporter. It's moving two things in the same direction. It's moving X and S inside of the cell. The movement of X, well, in this case, movement of X, well, that's a smiley face. That's favorable. Movement of S is frowny face. But when you combine these two, movement of S and movement of X, you get the overall thing to be positive. So that's why this is secondary active transport. So the movement of S is a secondary movement that's secondary to the active step of moving X. Okay. Now, our last kind of classic example of a membrane protein that lots of people are familiar with is the sodium potassium pump. Now, what these proteins do is they move three sodium ions from the inside of the cell to the outside, and they replace it with two potassium ions into the cell. Okay, so in the net of all of this, we're moving three sodiums out, two potassiums in. Okay, in order for this to happen, there's a series of steps. I always like to start right here. And that is where our enzyme E1 has bound three sodium ions. As soon as it binds those three sodium ions, then it's ready to bind ATP. And when it binds that ATP, it's going to hydrolyze that ATP and phosphorylate itself. It's going to take on one of those phosphates. So that phosphorylated version of our protein that is bound to three sodiums can now undergo a change in which those three sodiums are now displayed to the outside of the cell. They are released. Our protein is no longer E1 because it's no longer bound to the sodium ion. It is now E2, but it remains phosphorylated. That new version of our protein is ready to bind two potassium ions. That new version of our protein that's phosphorylated with two potassium ions is now ready to undergo a hydrolysis where it gets dephosphorylated, loses that phosphate. Our new form of our protein E2 still exists. It's bound to two potassium ions. It undergoes an inversion or a change in structure so that it can release the two potassium ions on the interior of the cell, effectively neutralizing almost the charge difference that we acquired when we lost those three sodium ions. Now, E1 is our enzyme that is ready to go again. It's ready to bind three sodium ions, ATP, and so on, and go through this process all over again. Now, E1 is a version of our protein that has a low affinity for potassium ions, but it has a very high affinity for sodium ions. E2 has a low affinity for sodium ions and a high affinity for potassium ions. I always kind of think about this as it's analogous to, well, our it's just the structural difference in the protein that what does it favor binding? Does it favor binding sodium or potassium?